Hello guys, today we are going to talk about triple integrals. Before this we have talked about the single integrals of functions of one variable and double integrals of functions of two variables. But today we will be talking about the triple integrals for functions of three variables. So before anything we will just see the simplest case where our function is defined on the rectangular box where b is equal to x, y, z, three components, it's three dimensions, right? And our x is ranging from a to b, our y is ranging from c to d, and our z is ranging from r to s. So the first step is to divide b into sub boxes. We do this by dividing the interval ab into I intervals. So xi minus 1 into xi for equal width, that would be our delta x, right? And dividing CD into m intervals of width delta y, and dividing RS into n intervals of delta z. The planes through the endpoints of these subintervals parallel to the coordinate planes divide the box B into LMN sub-boxes. So our sub-box would be something like Bijk is equal to xi minus 1 xi into yj minus 1 yj into zk minus 1 zk. So you can see that this is going to be a sub box, and we will be finding the volume. You can see the delta volume is equal to delta x, delta y, and delta z. That is going to be a volume of our sub box. So then we will form the triple Riemann sum. You remember before this we talked about the single Riemann sum, then we talked about the double Riemann sum, and there we go now. There's triple Riemann sum, and in this Riemann sum we can find LMN, right? We can find the summation of L, summation of N, and summation of N. And we will have our values over here in the brackets are f of xijk, yijk, and zijk, and it will be multiplied with the delta volume. Delta volume would be the volume of those sub boxes. So our sample point would be in this form, as in Bijk. So by analogy with the definition of double integral, we define the triple integral as the limit of triple Riemann sum in equation 2. It is similar to the double integral Riemann sum, and we can recall that, and we can see that in the double Riemann sum it was summation of m and n, but here we have summation of L as well. Okay, so definition 3, the triple integral of f over the box B is, how do we gonna write it down? So we will be writing it triple integral of b f of x comma y comma z dv is equal to limit lmn approaches to infinity, where we have summation of L, summation of m, and summation of n, and we will have our values I is equal to 1, j is equal to 1, and k is equal to 1, right? And then we will have our f of x, y, and z with the volume, with the delta volume, right? And if this limit exists, again, you know, the triple integral always exists if the function is continuous. We have to know that in the rest of the previous cases we talked about in our previous classes, in the double integral, in the single integral, we had one condition that our function has to be continuous, and that's what we apply over here. Function has to be continuous in this situation as well. So we can choose a sample point to be in any point in the sub box. It could be any point. We can say that like we were talking about the double integral, we said it could be upper right hand side, lower right hand side, upper left hand side, or midpoint. Same goes over here. It can be any point, but if we choose it to be the point xi, yj, and zk, we get a simpler looking expression for the triple integral, and that would be something like this, where we can see that triple integral of b f of x comma y comma z into dv is equal to limit where lmn approaches to infinity, and then we can have our summation n f of xi yj zk with delta v. So this is gonna be our equation for triple integral. Just as for double integrals, the practical method for evaluating triple integral is to express them as iterated integral as follows. So you remember we talked about the Fubini's theorem of double integral, and in Fubini's theorem of double integral we were finding the area along with AB into CD, but here we just have slight addition of RS, that is our z dimension, right? So if our function is continuous on the rectangular box, b is equal to AB into CD into RS, that is x into y into z, then our equation would be something like this, where we will have triple integration of b f of x comma y comma z dv is equal to, now here you have to look it carefully, where integration of r from r to integration is from r to s, integration from c to d, integration from a to b, f of x comma y comma z dx dy dz. So this is the iterated integration on the right hand side of Fubini's theorem. Now we can see that if we have to go from inside out, right? Remember, same thing we applied in our double integration, we have to apply in our triple integration. So we have to go inside out. First with respect to x, keeping y and z fixed, we will just treat y and z as constants, and then we integrate with respect to y, we will keep the z fixed and we will just treat it as constant, and finally we will integrate with respect to z. So this is how we're gonna apply our Fubini's theorem over here. There are 5 other possible orders in which we can integrate, all of which give the same value. For instance, we integrate with respect to y, then z, and then x. So what do? We will have our order like this. We're gonna write our equation in this form so that we can write dy, dz, and dx. That means we will first, that means we will be treating our equation in this way. We will integrate it with respect to y first, then we will integrate it with respect to z first, and lastly we will be integrating it with respect to x. Okay, now we just move to an example. An example, it says that evaluate the triple integral b x y z square into dv, where b is the rectangular box given by, and here we have the values for b, that is b is equal to x, y, z, where our x is greater than or equal to 0 and less than or equal to 1, and y is greater than or equal to -1 and less than or equal to 2, and z is equal to greater than or equal to 0 and less than or equal to 3. So just give it a try. You have to simply put the values first, right? But before that you have to give it a try for a graph. You have to just draw a graph, and then you have to apply these values into the integration method. So you know that how you will integrate them first. But remember one thing, whenever you are going to apply the integration method, you have to integrate the variables. When you can see the variables with respect to x, y, or z, you have to integrate them first. If you see the variables in the x with respect to x, or you see the variables with respect to y, you're gonna If you see two variables with respect to y, you will be integrating with respect to y first. If you see three variables with respect to z, you're gonna integrate with respect to z first. That means the maximum variables you have, you will be integrating that particular value first, right? And your last integration would be on your constants. So please just give it a try. All right, guys, so coming up with a solution, we could use any of these 6 possible orders of integration. All right, so if we choose to integrate with respect to x, then y, and then z, what do? We will obtain something like this, right? Because we have these particular values over here, we have all constants, we don't have any kind of variable over here, right? So we have triple integration of b x y z squared into dv is equal to integration 0 from 0 to 3, integrate from -1 to 2, integrate from 0 to 1, xyz squared dx dy dz. So it says that first of all we have to integrate our dx from inside out, right? Then dy, and lastly we'll be integrating our dz. So first we just integrate our dx with respect to x, we integrate it, and what do? We find value something like this, in which we are just integrating our x and we are not treating y and z as variables, we are just treating them as a fixed constant values, right? And here we have x is equal to 0 and the upper limit is x is equal to 1. In the next step we can see that we are finding okay, now we can see over here yz squared by 2 dy dz. It means that now we are going to integrate it with respect to y, and when we integrate it with respect to y, sorry guys, my bad. All right, so you can see over here when we integrate it with respect to y, our lower limit for y is equal to -1 and the upper limit would be y is equal to 2, right? After integration we will find something like this, integration 0 to 3, 3z squared by 4 dz. Now lastly we will be integrating it with respect to z, and we will find our answer as 27 by 4. And it's a simple integration, but we have to keep in mind we will not running for the shortcuts, so you have to go through the proper channel, you have to just write down each and every step, because that's a tricky part, especially when you are integrating for triple integration. That's a tricky part. So what do? We will find our answer something like this, 27 by 4, right? Okay, now since we defined the triple integral over a general bound, before that we were talking about a rectangular box, right? Now we're going to talk about this triple integral over a general bounded region E in 3-dimensional space. Okay, so what do we have over here? We will just recall our method that we applied in our double integration, or we can say the double integrals, which was we had a shape and then we had a rectangle, and that shape was enclosed in that particular rectangle, right? And we had a condition over that if particular shape lies in that rectangle, then our action of this particular function, capital F, would be equal to our smaller f function. But if it lies outside somewhere, that would not be equal to our function f, or it would be equal to 0, right? So what do? We enclose our E in a box P for the type given by equation 1. Then we define our f, capital F, so that it agrees with small f on E but is 0 for point in B, they are outside A. So when we just come straight away to the definition, it seems like if this particular area comes in that particular rectangle, it would be equal to our capital F of x comma y comma z dv. But if it goes away or it goes out, it lies outside, then it would be equal to 0. It will not be equal to our particular function. So our triple integral has essentially the same properties as a double integral. Our properties are almost same, right? We restrict our attention to continuous functions f and to certain simple types of regions. Okay, now the solid region E is said to be a type 1. Okay, now we have to see what is the type 1 over here, because we remember when we were talking about double integration, we had two types. Remember, one was a type 1 and the other one was type 2. And in those types, we had some sort of identification. If we have those vertical boundaries, right? That would be our type 1. If we have the horizontal boundaries with the help of constants, then we can say that's a type 2. But here we have type 1 if it lies between the graph of two continuous functions of x and y, right? If it lies between the graph of two continuous functions that are x and y, right? So our E is gonna be equal to, E will have three components, x, y, and z, right? Our xy would be belonging to our D. That means it would be lie in D, and our z value would be equal to or greater than u1, which is a function of x comma y, and our z would be less than or equal to our u2, that is a function of xy again. So where D is the projection of E on the xy plane as shown in the figure 2. So here you can see that D is a projection actually on the xy plane. We can see this on the xy plane over here, right? And then we can see the limits. The upper limit is u2 and lower limit is u1. That is the value of z, right? So that's type 1. That would be called type 1 if it lies between the graph of two continuous functions of x and y. So these are the two continuous functions of x and y, u1 and u2. These are the two continuous functions of x and y. Well, moving ahead, notice that the upper boundary of the solid E is the surface with equation z is equal to u2 x comma y. While the lower boundary is the surface z is equal to u1 x comma y. As we mentioned before, it would be like we will have two boundaries, upper and lower, u1 and u2 respectively. By the same sort of argument, it can be shown that if E is a type 1 region given by equation 5, then we will have an equation 6 which will be something like this. We will have our triple integration of E where our f of x comma y comma z would be multiplied with dv, and it would be equal to double integration of d, and then we will have our this integration inside where we will have two functions. Our lower boundary would be u1, that is a function, and u2 would be our upper boundary, that's the other function of x and y, and we will have our dA, which is the area outside. The meaning of the inner integral on the right side of the equation 6 is that x and y are held fixed. It is same thing. X and y would be held fixed. Therefore, u1 and u2 are regarded as constants. So they will be actually treated as constants, while f of x comma y comma z is integrated with respect to z. In particular, if the projection D of E, we can see the projection D, right, in the xy plane, and we can see that this particular surface of E on the xy plane is type 1 plane region. So we will just simply call it type 1 region when we will have this particular condition. We will have our projection on the xy plane, and then we will have two particular functions, that is u1 and u2. This would be actually our type 1 plane region. In particular, if projection, so what do we have in addition? We will have one more thing, that is our E would be having xyz, three components again, right? But our x would be greater than or equal to a and less than or equal to b, whereas our y would be greater than or equal to g1 of x, which is a function of x, and less than or equal to g2 of x, which is another function of x, and these functions would be continuous, right? When it comes to the z value, it would be greater than or equal to u1, which is a function of x and y, and less than or equal to u2, which is another function of x and y. And then it makes an equation 7, where we can see that there is an integration a to b, and integration g1 of x to g2 of x, and then integration u1 of x comma y to u2 of x comma y, and then we will have our f of x, y, and z, and dz, dy, dx. It means that we will be integrating our dz first, then dy, and then dx. It means, since I mentioned that when we will have the variables, we can clearly see that here we have two variables, x and y, with respect to z. So it means we will integrate these first, and we have one variable out with respect to y. So it means we will be integrating this on the second, and here we have constants with respect to x. So we will not treat them. We will just integrate them lastly, right? So this is the rule. We have to integrate the constants lastly, and the maximum number of variables would be integrated on the first and priority basis. Okay, on the other hand, D is a type 2 plane region. All right, now here we have a D, which is type 2 plane region, right? So what is changed over here? We can see that our C is less than or equal to y, which is less than or equal to d, right? And our x is greater than or equal to h1 of y, which is a function of y, and less than or equal to h2 of y, which is a function of which is another function of y. And our z value is less than or equal to greater than or equal to u1, which is a function of x and y, and less than or equal to u2, which is another function of x and y. So here we can see that, we can clearly see that when we have the surface over here, we have this D surface, right? And we have one variable over here. With respect to x, we have a variable here, and now we have switched our dx with dy, since we don't have any variable in our y value, or let's say we can say it, we don't have any variable with respect to y, so we will be integrating this lastly, and we will integrate our with respect to x on the second integration, and the first integration would be on the with respect to z, because we have two variables. Determining type 2, we should have our x value that is greater than or equal to u1 and less than or equal to u2, and y and z are actually u1 and u2 are functions of y and z, and y and z belongs to D. All right, so we have this projection D, and opposite to that we have our shape E, right? And we can see the upper limit is u2, and lower limit is u1, and these are actually the functions of y and z. We can say the back surface is u1 and the front surface is u2, and we can just write it down as equation 10. It would be double integration of d and then integration from u1 to u2 f of x comma y comma z into dx and then dA. So it clearly tells that we will just have our functions over here and we will integrate them with respect to our functions, and then later we will apply rest of the integration. So finally we have a type 3 region in this form. Now how do we determine this type 3 region? We have to know that we will be having our y value over here. That would be our y should be greater than or equal to u1 and less than or equal to u2, where u1 and u2 are the functions of x and z, and d is a projection of E on the xz plane. Y is equal to u1 in the left is the left surface, and y is equal to u2 would be the right surface. As you can see in the figure over here, this is the type 3 region, right? And we can see our left and right surfaces, that is u1 and u2 respectively, and we have our projection D over there. For this type of region we have this particular equation, that is equation number 11, and we can see that our dx have been replaced with dy because we are going to integrate our dy first, because we have two variables over here with respect to y, and we can see our integration from u1 to u2 goes there, and two functions that are functions of x and y, x and z actually. So in each of equations 10 and 11, there may be two possible expressions of the integral depending on whether D is type 1 or type 2 plane region. Okay guys, now just quickly going to our applications of triple integrals. So here we have to recall one thing, that the single integral of a to b f of x dx represents the area, right? We remember that whenever we have to find the area under the curve, we have to integrate in this with the help of this formula, right? And if we want to find the volume, then we will have a formula for the double integration, that would be double integration d f of x comma y dA. That will represent the surface, the volume under the surface z, right? And it would be above our d. The corresponding interpretation of a triple integral E f of x comma y comma z into dv, where our f of x comma y comma z is greater than or equal to 0, is not very useful, because it would be a hypervolume of a four-dimensional object, and of course that is very difficult to visualize. Okay, so what do we have but the triple integral, that is triple integration E f of x comma y comma z dv, can be interpreted in different ways in different physical situations depending on the physical interpretations of x, y, z and f of x comma y comma z. Let's begin with the special case where f of x comma y comma z is equal to 1 for all points in E. Then the triple integral does represent the volume of E. So here we can see that volume of E is equal to triple integration of E into dV, right? That is our equation number 12. For example, you can see this in the case of type 1 region by putting f of x comma y comma z is equal to 1 in formula 6, remember. Now we just put 1 over here, and what do we get? With the integration, we will be finding that our u2 of x comma y minus u1 x comma y into dA. So we know this represents the volume that lies between the surface z is equal to u1 and z is equal to u2. Alright guys, so now we just head towards example number 5. In this example, it's a really interesting one. It says use a triple integral to find the volume of a tetrahedron T bounded by the planes x plus 2y plus z is equal to 2, where x is equal to 2y, x is equal to 0, and z is equal to 0. Right? Now you have to find the triple integral in order to find the volume of the tetrahedron. So first of all, you have to just draw xy plane, right? And with the help of xy plane, you have to jump to the xyz plane, and you have to see how this tetrahedron works actually. Alright guys, so just jumping towards the solution, the tetrahedron T and its projection D on the xy plane, and show in the figure 14 and 15. So it says that first of all we have our values over here, right? So it's when we just simplify the values over here, we put x is equal to, we just substitute our y and z equals to 0, then we will be finding our x is equal to 1 over here. You can see on the x-axis it's from 0 to 1, and the y-axis from 0 to 1, right? Similarly, we will have our, we'll substitute x and z to 0, and we will find 2y is equal to 2, and it would be having our y is equal to 1 over here, right? So after just getting all these values from here, what do? We'll be going toward the lower, we will see the lower boundary of T is the plane z is equal to 0, and the upper boundary that we will have in our this particular question or statement, that is x plus 2y plus z is equal to 2, that is z is equal to 2 minus x minus 2y, right? So what do? We will find the volume of our tetrahedron, that is equal to triple integration of T into dV, right? So simply we, as we know that according to the rule, we have to, first of all, we have to see how many variables we have in our particular x, y, and z's. So according to that, we will just integrate with respect to our z, y, and x, right? So if we have constants in x, y, or z, we will just do that integration lately or lastly. But before that, we have to set it in a proper order, right? So here we can see that we have, in the first integration we have constants, right? In the second integration we have one variable and one constant, but in the third integration, that would be the first integration when we will start integrating them, because it would be from inside out, right? So it could be having, surely it's having two variables, right? From 0 to 2 minus x minus 2y. It means that we have to integrate this first with respect to z, then we have to integrate the second integration with respect to y, and lately we will be just, the lastly we'll be integrating our x values. Okay, so when we just simply okay, here we go, we find this particular equation when we try to integrate with respect to z, right? And that would be equal to 1 by 3. So you have to just go through by step, but carefully. All right, you have to know the proper pattern. If you will not follow this particular rule, you'll be in a big trouble, because integrating for three triple integration, that is really a big deal, and you will not put your focus on. All right, guys, so that was all from the triple integration. If you have any kind of question, we will jump toward our question and answer session, and we will have a healthy debate over there.